Okay, so in terms of LCN facility, so the LCN is a sort of virtual entity bringing people together from across London, King's College, UCL, and Imperial College. Now focusing on the Imperial side for this, so there are different types of facilities across the LCN. Those that were acquired as part of the LCN being built up, and the Titan microscope that's shown here is one example. And then there are other facilities that were present before the LCN, but that are used to support LCN activities such as X-ray diffraction that Richard Sweeney will talk about. And then there are the facilities that have come on after the creation of the LCN, and that the LCN has supported in demonstrating a need across London as well, and so by engaging the community. So here, these presentations will focus on the facilities at Imperial, on some of them that are available on charge out, and here are here is a link that can be used to access this charge out. So this is the practical way in which you can book the facilities and pay for them. They can be accessed by Imperial users, but also by external users from our LCN partners at UCL and King's College. And please contact facilities managers if you get stuck. So today we focus on 5 facilities, but there are many others. And so the purpose of these spotlight talks will be to really identify those facilities that can be shared across the LCN community in a very easy way. So I'm hoping that this, the message is also that the facilities are available to UCL and King's College members, but that also means that the inverse is true too. So for our Imperial community, there is a whole host of facilities available at UCL and King's College, and here are some bullet points here that summarize generally the type of facilities that are available there. But there is on the left-hand side here, you see the London Nano website is still being refreshed, but it does contain a list of equipment that you can look through, that you can filter through from technique or institution as well. So you can search through that and find ways in which you can support your research. Okay, so we have a very packed schedule of 5 facilities on Spotlight today. So I will stop here and leave the floor to our speakers. We will leave questions to the end of the presentations if there is any time left. And as I said, feel free to get in touch if you've got any further questions as well. So I hope you enjoy these presentations, and thank you very much to all the research facilities managers in advance for giving those presentations. So let's start with Dr. Mahmoud Ardakani on electron microscopy.
I would like to appreciate all the leading academics that through a number of years supporting the electron microscopy facility by providing and helping finding money to keep our facility up to date. So we do have a modern facility now, and we try to keep this facility as up to date as possible, and it will going to continue. As Sandrine mentioned, is open to college, Imperial College, and other collaborators. The facility was part of materials department, but now is central facilities. So we do support industry as well, but the return is not very quick because the priority is our students and researchers that we have and we collaborate with. Now, I'll just go through some of the facility that we have. The picture that you see is atrium of the microscopy suite. It's not always tidy like that because we get parts for a replacement and so on. So always we got bits and pieces in the corridor. We do have 3 transmission electron microscope. One Titan which can operate at 80-300 kilovolts. It is FEG STEM. I'll go to the pages later on and explain one by one a little bit about what we can do with this microscope. And then we have two Joule microscope. One of them is FEG and the other one is Lab 6, 80 and 200 kilowatt operations that we have. Two field imaging gun, SEM, Sigma 300, Leo 25. This is the oldest microscope that we have. I think it's about 15 years old, but it still is a very, very valuable microscope to us. We can do a lot of high resolution microscopy. These are all Zeiss microscope. And then we have two FEG SEM. Auriga is a Zeiss and Helios is Thermo Fisher nowadays. It used to be FEI. We have one FEG eSIMS. This is our environmental SEM, which is called Quanta by FEI or Thermo Fisher. We have Raman spectroscopy as well that we can use. And then we have two little SEMs. These are a standard Lab 6 filament that we use for training purposes or for undergraduate, or even some of our PhD students can use. And then we got a range of ancillary equipment that attach to these microscopes. So a couple of images from our Titan. This microscope was initially bought to give us very high resolution chemical analysis capability. And then we wanted to use it for electronic materials. But nevertheless, it can be used for other materials, provided that the sample is the correct samples. Okay, with this microscope, we could have energy resolution, if you want the chemical analysis, of about 0.6 eV. We do have monochromator on this machine, so we can achieve that sort of chemical resolution. This is almost atomic resolution. We do have EDX detector on that. We have an EELS detector on that. And I've shown a couple of images here for doing chemical analysis at atomic resolution. And one STEM image here from silicon that you can see these dumbbells on silicon. And then you can see that we can resolve 0.36 nanometer. So that's, as I said, this is for silicon dumbbell that, you need to be patient to get this sort of images. It's not saying that you put the sample inside and you get that. I mean, it needs a lot of effort and patience to prepare the sample to start with and be able to do this chemical analysis at atomic level. Okay, I'm just going to move to next sample, next microscope. Okay, this is our latest transmission electron microscope, Joule 200 Plus. We use this microscope for most training. If people haven't got any training or experience with TEM, this is the entry level for us. This is about 3 years old microscope. We can do high resolution imaging. That's one example, looking at titanium and titanium oxide, and you can see nicely resolved lattice. We do have a STEM detector on that. This image number 3, letter 3, is a work by, sorry, I forgot to put the name of these contributors. I have to find their names. I just picked up from the microscope. This is a STEM image from a titanium oxide that you can see pile of the dislocation there. And you got the core shell structures for some silicon shell, silica shell structures. So very versatile microscope that we have. We do have cryo-TEM. We do have cryo station that if some people are interested to do some cryo-TEM, we can do this cryo-TEM on these samples. So EDX STM and cryo-STM, cryo-TEM or STM can be done on that microscope. Our next microscope is Joule 200 F8200 kilowatt STEM. The filament is FEG, so the resolution is much better. We can do many work as we could do on FX2 2000 plus. Plus, we have a better resolution here. On this microscope, we have a GATAN system for doing EELS and HARAF. These are high-angle dark field images. And at the same time, we could do EDX analysis. The example which I'll show you here is doing a mapping on a sample that has got multi-component. I'm showing just silicon and oxygen here. So it's very versatile microscope to do EELs, to do EDX, and to do high-resolution imaging. The operation of this machine is very, very similar to 2000 plus. Is a slightly older microscope, and the software is slightly different. But once people get trained on 2000 plus, it is very straightforward for the users to be able to use this microscope. Okay, so now I'm going to our SEMs. First is showing our oldest microscope size that we could resolve the particles about 5 to 10 nanometer here. This is a nickel super alloy that we are interested to look at the gamma prime particles. This machine is equipped with the EDX detector by AXO instrument. We can have X-ray map of the chemical analysis of the samples here. And also this microscope is heavily used for studying the of films, fibers on substrate for solar cells and other experiments. So it's heavily used, this particular machine, for high resolution imaging. It's got very low probe current that help to get surface electron, and then it will help to get a good resolution. Our ESAM is Quanta. We do have Raman attached to this microscope. The Raman can be used separately or can be in conjunction with our Quanta SEM. We do have chemical analysis, EDX, and EBSD by Bruker. And there are a number of test kits that we could add to the stage, doing some high temperature testing, doing mechanical testing, as well as doing cryo testing. So it's a research machine that we can call this machine. It's a lot of attachment that we could add and make a very useful tool. And again, a couple of examples of high resolution EBSD that we can see the distribution of a strain around the nano indenter. And then this is a nano indenter that we can attach to this microscope and basically compress these nano features and measure the elastic property of these sample. This is our Zeiss FIB SEM. This is a field emission FEG SEM. Very useful tool to do imaging as well as the other SEM. Plus, we got a FIB attachment here. We can do a slice and view, and we can reconstruct by a specific software that we have in our EM suite to reconstruct the 3D view of the samples. Also, this microscope has got very good in-lens detector. This is, we call it selective energy select detector, that you can look at very fine details in biological samples. The example that you see here is growth of cells on some nanoneedles, and our researchers are interested to slice these stem cells and look the interactions between these needles and the cell itself. Okay, so again, this machine has got a very, very good resolution in terms of imaging with the second electron image, backscatter electron image. We do have lots of attachment for this machine, EDX and FIB, and I said some platinum deposition. If someone interested in platinum deposition, is possible to do. Okay, our next FIB is FEI, or Thermo Fisher's Helios. This is the oldest FIB that we have, and this basically purchased when we bought Titan. Initially, this machine was purchased to making samples to support Titan. So we do have capability of making lamella for TEM, and also we got the capability of doing some slice and view and 3D reconstructions. It's an example of 3D reconstructions of some nickel samples we have here. nano indentations that we can do, and in the examples, and you can cut the samples for TEM analysis. Okay, and this is the map of the campus. So we are located in this corner of the South Kensington campus. If you are interested to visit our lab, you can basically arrange a time at this time of year that we got COVID-19. We can meet you at electron microscopy back door here if you want to drop the samples, or we can meet you at the entrance to the department. Now, the leading academic is Finn, and also the other academics helping with our EM suite. I am basically the research facility manager for most of the equipment. Catriona is looking after our EEL system and Titan, and Cathy is helping us with other equipment, as well as looking after the Helios sample preparation. If you have one or two samples that you need to prepare, it takes a lot of time for you to get trained, but Cathy will be able to make the sample for you, and then we can do the PM analysis. I hope I managed to go through this quickly to show you what we have, and thank you for listening.
Thank you very much. Thank you very much, Mahmoud. That's great. So lots of facilities to cover within this EM presentation. So thanks very much for giving an overview. So we, in light of time, we'll move on straight away to the next one, which is by Gwilherm. And if there are any questions, we can maybe take them at the end or deal with them by email. So thank you. So next one is focused on the Advanced Photoelectron Spectroscopy Lab by Gwilherm Kerherve. Thank you.
So it will be a shorter presentation than the electron microscopy one, because the APSL lab is new, is about 6 years old, and we have a lot less instruments. So this is the Advanced Photoelectron Spectroscopy Laboratory, also called APSL lab, and we have in our lab 4 XPS. The 2 ambient pressure XPS, one for clean samples, another one for dirty sample, and we have an angle resolve photoelectron spectroscopy, also called APSL, and most importantly, because this is actually the only one available to users, is the high throughput XPS. Okay. So this is what I was saying is the 3 other XPS are available through collaborations with David Payne, and so those consist of the 2 ambient XPS and the angle resolve XPS. But the high throughput is available to all CDTs and all Imperial College users, and it has the capability of having a variable X-ray spot between 30 to 400 microns. It has a tilt module to measure the topmost surface and surface of your samples. It can also measure work function and do depth profiling through sputtering. So then those are the 4 different types of sample holder. The standard sample holder shown here can have up to 9 samples, but I have of size 2 centimeters, but I've seen people putting 20 samples on it. So you can in one go measure up to 20 samples. For work function measurements, you have this type of sample holder, which has a gold reference to be able to measure the Fermi edge of the gold, so you can calibrate your work function. And then if you need to do the tilt, so to measure the topmost surface, you have a tilt sample holder that can go between 0 and 80 degrees. If you have samples that are in glove box, then you can transfer your samples between your glove box and the XPS using this vacuum sample holder, and your sample will not see the air, will not be contaminated with air. So any request is done through by email through me, and all you need is that you provide samples without free of iodines and fluorine. You also need to provide a cost form, and you need to be registered on PPMS. And then we'll decide if you get a training, or if I measure your samples to drop off, or if for experienced users or trained users, you get the measure done by yourself. So here I will present just two examples of research that has been done on the XPS. But so this year I've counted about 30 papers that's done, but this is just two of the papers. This is one done by Ardakani, so in Applied Materials Interface, in which he studied the observations of iridium nanoparticles from STO. So in here you see the iridium doped STO, the perovskite, which has been reduced then through in a heating. Oh, sorry, it has been heated in a reducing atmosphere, and then you get nanoparticles. And on the right side here, you see the iridium 4F core level, in which in the STO you see a titanium 3 aspects, but then when you doped your STO, you see iridium 3+, and after reduction through heat, you see the formations of metallic iridium that increase with increasing heating. Okay, and this was the proof of having metallic nanoparticles on top of the surface. Another paper, which has been published by Pina in Nanoscale Advance, and this was to do some Ceria nanoparticles which were functionalized by fulleropyrrolidine, also called Si-FULP. And what they've done is they've used the polycondensation process, and those were functionalized. The Ceria nanoparticles were functionalized, and XPS was used to prove this functionalization. Our measure cerium 3D that you see here. This is the on the left side. This is the non-functionalized cerium nanoparticles, and you can see 10 peaks, some in red corresponding to the cerium 3+, and some in gray to the cerium 4+. And once you functionalize, you see an increase of the cerium 3+. So this was a proof that that you have functionalized the cerium nanoparticles.
Very much, Gwilherm, for providing those great examples of XPS and giving the procedure. So we'll move swiftly on to Cleanroom and Nanofab lab that is now based in physics, and David Mack is presenting this now.
Hey, thank you. Thank you for inviting me to give a quick introduction to the facilities in EXS, which is a group in the physics department at Imperial College London. So I work there as a technician, and let me just try and share my desktop. And I'd like to give you just a really brief intro into the kind of work that we're doing there and the facilities that we have available. Can you see my screen?
Yes, this works. Thank you.
Yes, fabulous. Okay, so so I'm going to take you through two laboratories that we have there. One is the Nano-Fabrication laboratory, and one is the experimental solid-state clean room. And just have a look at the equipment in there and what's available and what kind of work we're doing there. So this is the first. We'll look at the Nano-Fabrication laboratory, and this is obviously a laboratory focused on fabricating plasmonic and nano antenna for our research there, and the main workhorses in there are two Wraith E-line systems. One is in fact eventually going to head to materials, and so we'll be on the White City campus, but currently it's being housed inside our laboratory. So both of these systems work from 5 to 30 kilovolts, and they can achieve and via electron doing electron beam lithography, they can achieve feature sizes of around 20 nanometers and gap sizes of around 10 nanometers for the designs of antenna that we're making. These are like commonly achievable feature sizes and gap sizes, but you can push features and gaps smaller than this, but it becomes less and less reliable as you do so and becomes more and more fiddly. They have 100 micron write fields, and you can do reasonably large area samples, but obviously as your sample sizes increase, the write times start to get extremely long as well. Here's some examples of some of the structures that we've made using the lithography systems there. So we've got some trimer antennas with gap sizes of between 10 and 20 nanometers. We've got some broadband here, which is on the top left. We've got some trimer antennas in the center. We have some broadband dimer antennas, and then just like various other shapes and some gratings down on the left, and some dots within rings down on the bottom right. So this is all done using electron beam lithography. We have access to a variety of electron beam resists to suit various purposes. And then here's an example of these are slightly larger area structures. So these are nanomagnetic structures. So we pattern them using electron beam lithography, and then the material, which is, in this case, it's a permalloy, is deposited afterwards. And then you get these large lattice structures, which are used to make artificial spin ices in our magnetic part of the experimental solid state group. So another patterning technique available to us in the nanofabrication lab is a direct optical lithography system. So this is basically a confocal microscope setup that uses multiphoton absorption to give confinement within photoresists, which allows you to write in 3 dimensions inside a photopolymer, which means you can make, instead of as electron beam lithography is a layer by layer process. So everything's in 2-dimensional layers. You make one layer, and then if you want another layer on top of that, you have to design that and then do it in steps. This you can write. Continuously and in all directions. It can also do 2D photolithography without a mask, which is quite useful if we're intending to do something once or twice and we don't want to send off for the cost of a mask for conventional photolithography. So here's an example of some of the structures that you can make with this system. It has a sort of a resolution limit of around 250 nanometers. So it's called a nanoscribe. The naming may be slightly spurious, but 250 nanometers is reasonably good. So we've used it to make things like these photonic cages. So these are photonic cages supported on blocks. And this is written in the photopolymer. But you can also then metallize these structures if you need to. And this is a paper by Stefan Meyer's group on these photonic cages. But you can also make things like photonic crystals over here on the right. And here's some more examples of stuff that is possible to make with this nanoscribe, a 3D printing system. These microfluidic, we do make also microfluidic nozzles with this printing system as well. But you can also make like pharmaceutical, like needles and MEMS systems as well. This is a quick example of something that we've recently put together with it. These are just some basic waveguides that stand out from the substrate in a 3-dimensional manner, such that you can couple with a standard optical microscope into these waveguides to like move light around a circuit. So this is something we've been looking at. But also we commonly make things like these 2D. This is an example on the right of 2D photolithography, and this is something that we make commonly. So this is like a connector, so a connector pad to connect small-scale electronic structures within this square to large-scale electronic structures outside. Inside the Nanofab lab as well, we also have PVD systems, some physical vapor deposition systems. So we have thermal evaporation and sputtering with the angstrom system. We have the metal box, which is a converted Auto 306 Edwards evaporator that we use to do magnetic materials, and we also have a sputterer to do contacts and things like that. We have a small processing center in there for doing liftoffs and solution processing, and we also have an oxygen plasma usher. And then we have some microscopes and a microscope and an ellipsometry system in there. So it's kind of a lab that we've designed around nanofabrication for us to achieve that. We also have a tilting three-dimensional stage to look for in our SEM, so we can take angle, we can look at the sides of our materials. And then onto the clean room. It's an ISO plastics clean room that we have there as well. This is a separate facility, but I also manage that one as well. We have a collection of wet benches and various things to do, again, nanofabrication focused work. We have a photolithography system in there, which is the main patterning system. So it's just a mercury lamp, and it has hard and soft contact modes, and it can do up to 4-inch wave sizes. And we regularly get down to micron resolutions with it. It's not the newest photolithography system, but it does work, and we do regularly get some nice work out of it. So this is an example of some of the stuff that we've been making in there. So this is an organic transistor patterned with a combination of photolithography and electron beam lithography. So this person was doing work in the nanofabrication lab and in the clean room. And so these red sections are an organic semiconductor, and as you can see in here, there's an organic semiconductor. These fine lines are done with electron beam lithography, and the large lines are done with photolithography. Again, we're constantly making these large-scale contacts, and this is done with photolithography instead of with the maskless nanoscribe. So this is like standard photolithography. This is something that our bioengineering people are doing. So there's some people from other departments who've had access. So this is looking at cancer cell attachments in microfluidic chambers that they've built, that they've fabricated using photolithography in the clean room. We also have some more physical vapor deposition systems in the clean room. We have an Auto 306 evaporator, which has thermal evaporation and electron beam evaporation. And we have another sputterer in there as well. More characterization. We just have general like microscopes and digital scales for chemical work in there, like and observation stuff. We have some profilometers and some contact angle measurers in there as well. And in the chem lab, which is next to the clean room, which is part of the same facility, we have a gravure printer and some furnaces and DI water systems and stuff, which is useful for the work people are doing in there. And in characterization in there, we have some we have a spectrophotometer and a spectrophotometer to do reflection and absorption measurements and fluorescent measurements, respectively. Getting access is very complicated at the moment. We're currently in flux because we're transitioning from how we previously did things, which was all through contact with me and just sort of unique arrangements each time, to moving the whole thing hopefully to the EMS system, so that it will be a lot more accessible to external users as well, and make it easier to use internally also. So details to follow on that front, but please do contact me if you have any questions, if you'd like access. Hopefully in the next few months we'll move to that PPEMS system and everything will become a lot clearer. But there are other fabrication options available in the EXS. There's also a large glove box up on level 9, which has got thermal evaporators and various other things inside there for fabrication work as well. I hope that gave you some information on what's available in EXS in physics. So thank you very much for listening. And I think that's it from me.
Thank you very much, David. That's great. That's great tools for nanotechnology and nanoscience. Wonderful. So now we move on to thin film technology. So I think a bit of overlap as well with the Nanofab lab, but a different angle too. So so Peter Petrov will be giving the next talk, and I see he's getting ready.
So hello everyone. I am Peter Petrov. I run the thin film technology laboratory in the Department of Materials. So my presentation will be very short. So our lab was established in 2001, and since 2007 it's located in the Department of Materials. So it's a founding member of LCN, and since recently we are also part of Atom to Devices team of St. Henry Royce Institute. So, and in the the lab, we provide Imperial College and all LCN partners, as well as other academic and industrial partners with facilities for thin film depositions, device patterning, and electrical characterization. So in our lab, we have a lot of equipment. I'm not going to discuss any of our systems just for interest of time, but just so here is the list of all our deposition systems. So we have pulse laser deposition systems, we have magnetron spatters, we have e-beam evaporators. So we have CVD systems. So we have almost everything which you can dream for depositing thin films. Also, we have facilities for thin film patterning, and which includes two mask aligners, reactive igniters, wide beam annealing systems, and we have also facilities for electrical measurements. So it's not excessive, but it's more than enough. So we have cryo and room temperature probe stations. We have profilers. We have optical film thickness measurement system, and also a lot of electrical testing equipment. The access to all our equipment is via PPMS. So I believe all this presentation will be available. Clickable link to the instructions how to get enrolled to the TFT lab user list, or if this link doesn't work, there is a link which you copy paste. But if you wish, always email or call me. I'll be always happy to help. So a very quick overview of some of the main system in the laboratory. So our working horse is our PLD system, which has 4 separate chambers. Each chamber is equipped with 6-position target carousels, so we can make multi-layer structures with up to 6 different materials in situ. And one of our chamber is equipped with reed. So this is this system allows us to do layer by layer deposition with very, very high precision. Our other working horse is our magnetron sputtering system, which is combined with e-beam evaporator, but very soon we'll have another system which will be dedicated just for e-beam evaporation. So in here we have 4-inch sample holder, and which we could cover uniformly with various different films, different coatings. In our yellow room, we have 2 mask aligners, which allow us to make, which are combined, which are complemented with reactive ion etching and ion milling system. Now we're in process of purchasing 2 more ion milling system, and one is inductively coupled plasma. It's inductively coupled plasma reactive ion etcher. The other is ion milling system with reactive ion etching sources and chemical etching abilities. And here we could achieve easily micron resolution and micron and submicron resolution down to few nanometers. As I said, we have room temperature and cryo probe station, and which covered the temperature range from liquid nitrogen up to 200-250 Celsius. Also, the unique part of our cryoprobe station is the ability to apply perpendicular and horizontal magnetic field in situ with strain up to 0.15 Tesla. And this allows us to do various types of measurement. And just to wrap up, if you wish to get access to the Thin Film Technology Laboratory, please email me or just follow these links and you'll find the detailed instruction how to become a TFT Lab user. And before I finish, I like to thank the people who helped me running this lab, Dr. Binzu, soon to be Dr. Ryan Bauer, Andrei Barinov, Sami Ramadan, and the PhD students and other PhD students from my group, Zhao, Mohammed, and Yushuan. So at this point, I will stop and thank you for your attention. And if you have any questions, please ask me now or at the end of this event.
Thank you very much, Peter. That's great, and great to see all the infant growth there, and to make all our wishes come true. Excellent, thank you. And final presentation is by Richard Sweeney on X-ray diffraction.
Okay, well, good afternoon, everyone. I'm Richard Sweeney, and for my sins, I look after two facilities here, namely X-ray diffraction and thermal analysis. Previous speakers have mentioned how old their facilities, or rather how new their facilities are. I daren't tell you how old my facilities are, because it belies just how long I've been here. But what I intend to do is give you a quick overview of each of the two facilities, and then I'll pick out a few examples of what I think might be of use to you. So let's start with X-ray diffraction. And obviously in X-ray diffraction, we're concerned with the arrangement of atoms on normally a crystalline lattice. So probably the most obvious thing that you might want to do with X-ray diffraction is to determine the phase composition of your specimens. So you might want to know what your precursors are, or have you synthesized the right material. But X-ray diffraction is going to be the technique that's going to tell you exactly what phase or compound you happen to have to start with. And that is normally achieved with reference to a standard database. So we use a fingerprint type method to identify the phases present. That will work in crystalline materials. But an even easier thing that you can do is just determine whether you have an amorphous material or a crystalline material. That couldn't really be much easier. You don't have to do any analysis. You just look at your output. And if you get a broad amorphous halo, then it's amorphous. If you get sharp peaks, then it's crystalline. A combination of the two, then you will have two phases present, one crystalline and one amorphous. But then there's that grey area between amorphous and crystalline, where the crystalline size is getting smaller and smaller. And X-ray diffraction proves a really easy, quick, clean method to get an estimate of crystalline size by looking at the line broadening. So when you have crystalline peaks, they're going to be nice and sharp, but as the crystalline size gets smaller, it's going to broaden. And when you're down to about 100 nanometers, you will see that broadening start to occur. And then as the size goes down to probably 50 nanometers, you can probably get an estimate of the crystallite size. There you can do a calculation based on half width. But when your crystallites are down in the, say, 10 nanometer range, 1 to 10 nanometers, it's a brilliant technique. It's very sensitive, and it's very quick and easy to get an estimate of your crystallite size. You do need to remember that it's crystallite size that you're measuring here and not particle size. Often they're the same, but not necessarily. And it will measure your crystallite size in a specific crystallographic direction. So I would guess that those three are probably the ones that initially you might be more interested in. These other techniques that are offered are generally for solid specimens, and you probably aren't too interested in epitaxy or stress, but it's worth mentioning that those things are also possible. In terms of the equipment that we've got, we have a suite of 7 diffractometers, 5 full-size analytical instruments with different configurations optimized for different techniques, and 2 benchtop Bruker instruments for the routine type analysis, and quite an extensive suite of software for all the different analysis types. In terms of access, always an initial discussion with me. We need to discuss the feasibility and, very importantly, the safety aspects of your samples. Although you're dealing with X-rays, the hazard due to X-rays is completely mitigated by the control measures that we have in place. And the biggest risk, the risk to safety, comes either from the user themselves or normally from the user's samples. So it's your samples that provides the risk. And I have to mention that in both the X-ray and the thermal lab, there is a ban on bringing in any loose nano powders. So they are not geared up to have loose nano powders about. So part of our discussion must be to work out how we're going to fix your sample so that it doesn't become airborne. And that may be that you mount your samples in your lab and then contain them and transport them down to the X-ray and back again. It may be that we glue your samples onto a substrate or mix them with something like Vaseline or whatever. We have to come up with a method that enables us to fix your sample so it doesn't become airborne. Of course, if it's a solid, that's not a problem. It's really the powders. So it's very important that we have that safety discussion. And then as you're working with X-rays, there are some statutory requirements. You need to register as an X-ray worker, and you need to complete some online safety modules. And then once you've done that, then you can apply for task-specific training. So now here are what these things look like, and there's a lot on here. So let's just zoom in on something. These, for those who haven't seen them, these are what X-ray diffractometers look like. This is a benchtop module, which would be about 1/2 to 3/4 meter cube. We have the full, which are more like 1.5 to 2 meters cube. So these are big instruments. And when I mentioned earlier phase identification, this would be typical of a crystalline material, giving you these nice sharp peaks, and we will compare that with our ICDD database, and then you will get a definitive identification of the phases present, and in this case a mixture of phases. In terms of crystallinity that I mentioned, see how sharp these peaks are. Once they start broadening, then you know that you have a small crystallite size And as I said, once you've got really below 50 nanometers, then you're able to calculate it from the half widths. Residual stress is probably not something that you'll be too interested in. These are for epitaxial thin films where we can do reflectometry and reciprocal space maps. Here we can produce pole figures where we're looking at preferred orientation. Again, this will be in solid materials, so if you have films. And what may well be of interest to you is in situ methods. So we have a high temperature diffractometer that will enable us to do measurements at elevated temperatures and controlled atmospheres. So temperature is increasing as we go up here, and you can see that we start off with one diffraction pattern indicating a particular phase, and then we, at a certain temperature, we see an obvious phase change. And you could do this either dynamically by changing the temperature or isothermally as a function of or you could even change the atmosphere again as a function of time. Something that may be of interest to you, which is not exactly diffraction, but is, as its name implies, scattering. So SAC, small angle scattering, utilizes the region that we normally discard. When we're doing wide angle XRD, we probably only go down to a minimum angle of 5 degrees, 2 theta. But when you're doing SACs, you're looking at that region between about 0.1 degrees and 5 degrees. And we're getting a different sort of information. We're getting structural information on the nanoscale here. And it is possible in this case to get full size distributions rather than crystallite size distributions. And with the right modeling, you can even get information about shape of them. Now, SACS instruments are normally dedicated instruments, and they're quite large instruments. And this is quite a novel method because this is a relatively small attachment that goes on a normal diffractometer. And so it is possible that we can't quite as good results as you might do with a dedicated instrument, but nonetheless it works quite well. It does seem to work better when you've got good density contrast, and it's not particularly wonderful with CNTs. It depends what information you're looking for, but there's been mixed results on CNTs. Here's some examples of some more in situ experiments, and you can see here I've done multiple scans, and there's an obvious phase change here. We can see the shifting peak position as the lattice parameter changes as a function of temperature. We can do heating and cooling, and you can see that there's another phase change on the way down, which forms a different phase to that we started. That data set there took about 5 days to collect that data. This data set here was much quicker, and this is showing the development of crystallization in a glass ceramic. This is the substrate on which the sample is placed, so we're not interested in that, but you can see here this broad amorphous halo, which is due to the initial amorphous material, the glassy material, and then as we heat up somewhere between 350 and 400, we start to see the appearance of crystalline peaks, and then as we go up, the crystallinity develops. So that may be something that you might find useful. And now quickly, thermal analysis. In thermal analysis, you're just interested in measuring a physical property as a function of temperature. So if ever you want to know at what temperature something happens, then thermal analysis is the technique to choose. You might want to know when your precursor decomposes, or you want to know if your final product is thermally stable. then thermal analysis is the way to go. And so you can follow things like crystallization, phase changes, glass transitions, and decompositions, solid gas reactions. And generally, we have high temperature facilities. So all our equipment is capable of measurements up to 1500 degrees C. We don't have a subambient facility, and we don't even consider anything's warm until it's got to well over 200. We have two simultaneous thermal analyzers, so performing differential scanning calorimetry and thermogravimetric analysis simultaneously. And again, access, you need to talk to me about is the experiment you're proposing feasible? What sort of temperature range are you going to measure in? What atmosphere control do you need? Do you need oxidizing, or do you need inert atmosphere? We need to discuss the crucibles to make sure that you're not going to have any adverse reaction between your sample and the crucibles, and again, safety considerations of your sample. And these are 7-place balances. They are very, very delicate balances, so you do need a steady hand. And now just a bit more detail here. Again, these are what STAs look like. This is the furnace here and here. And these things will be about 3/4 of a meter cube in terms of their size. And an example here, we have temperature on the x-axis and mass here in green and the DSC signal in blue. We're just looking at thermal decomposition, and you can see the decomposition of calcium oxalate monohydrate goes in 3 distinct stages. And so again, if you want to know at what temperature can you take your precursor before it starts breaking down, then that's how you establish that. Over here, I'm showing you again another way at finding the presence of crystallization and what temperature it occurs at. So this is crystallization in a glass ceramic, and you can see the glass transition here, this shift in baseline, followed by the exothermic peak due to crystallization. And it is possible here, this is just isotherming a specimen, but then cycling the gases. So we're doing air and nitrogen, and we're looking at the exchange on the lattice and making sure it's reversible and making sure that there's no degradation after multiple cycles. So just to summarize in terms of you getting access, it's a simple 3-stage process. The first stage, talk to me. We need to discuss the limits of the technique. Is what you're asking for achievable? Is your sample in the right size range? Is it the right particle size? Is it a solid? What about the surface roughness? What about the size and shape of your sample? How can we handle that? Is it a liquid? Is it a solid? Is it a gel? Is it a powder? Most things we can handle, but not gases. Don't turn up to me with a gas. That's not going to work. Detection limits, you know, if you want to determine parts per million levels, that's not going to work. So we need to make sure that we can handle what you want there. And again, very important, the safety issues of your samples. The second stage, talk to me some more. We need to discuss what training you need. If it's for XRD, then you've got to fulfill the statutory requirements first, and that you do through me. Once you tell me you want to do XRD, I will handle all that and guide you through that process. And then you'll do basic training first so that you can do the routine techniques and instruments. But then you go on to multi-stage training for the more involved techniques. And some of the techniques you'll need to develop some handling skills, such as for the microbalances on the thermal equipment, or maybe capillaries for the sacs. And can you guess what the third stage is? Talk to me some more. We need to talk about timescale. and I need to manage your expectations. So to go from 0, I've never used an X-ray diffractometer before, to being able to do in situ methods is not necessarily a quick process in the best of times. But obviously with the COVID situation, some of our time frames will be extended. But again, talk to me and we'll discuss all those things. So I guess not to labour the point, but my general message is talk to me. Okay, thank you very much.
Thank you very much, Richard, for this closing presentation. Wonderful. So talk to Richard if you want to do any X-ray diffraction. I'm afraid we have run out of time. Although I must say I'm very impressed that we managed to get quite as much information in this hour. If you have any burning questions, feel free to ask, or otherwise get in touch directly with the facilities managers or me. So thank you so much to everyone who presented today. I think it's been really useful, both in terms of the science and the practical aspects. And we will continue on these presentations next year. The presentations will include spin lab and surface analysis, amongst others, but you will be informed in due time, and hopefully will be able to join as well. So I don't know if there is anyone who has any hand up, but maybe this is quite a lot to process. So I think also thank you, Richard, for mentioning the COVID situation. It is true that this will make everything a little bit more difficult, but there have been a lot of measures being developed at all the facilities to ensure that it is still possible, although slower, to get access and to get some science done. Okay, so thank you. I will leave it at that if there are no further questions. And thank you very much, and see you next time for the next LCN seminar or in various facilities labs. So thank you very much.